Assalamualaikum warahmatullahi wabarakatuh. Good morning. As I said in last week, today we will continue the new chapter after we finish the ordinary differential equation in last week. So the chapter is Laplace transform. So what is the Laplace transform? Transform is a mathematical conversion from one way of thinking to another to make a problem easier to solve. So it's like we have a problem. So the problem is in one domain. As we know that in our engineering, electrical engineering, there are many domains. It's like time domain, or we call it a domain T, or frequency domain, or maybe we call it domain omega t or seg omega t, and then yeah, another like a discrete. It is a discrete is time domain, also a frequency domain. So if we have a problem in one specific domain, like a time domain, so it's like we want to um, we want to analyze the voice, the the voice signal from one side, from transmitter to receiver. So the voice signal actually originally from the time domain, because if we make a voice, so it's like we produce a magnitude per time domain. But it's very difficult for us as an engineer to analyze the signal, the voice signal in time domain, because of if we want to cut in one or some frequency. It's like we want to make a filter, we want to remove a noise. So it's very difficult for us to analyze, to remove a noise, if we work in time domain. But it's very easy for us to analyze and then to produce, to design a filter, if we transform the voice signal from the time domain to the frequency domain, because the filter is based on the frequency. It's like we want to remove the low frequency, or we found that the noise in located in higher frequency, so we just we put the filter in high frequency and cut that noise. So it's a little bit easier for us to analyze, to produce, to whatever we want about the signal in frequency domain, actually in the voice, then if we analyze it in time domain. So the transform, Laplace transform is the best way how to convert from the one domain to another domain. Okay, so after we solve the problem in maybe for voice signal, we want to transform from domain time to the domain frequency, and then after we finish or we already finish our problem, so we transfer back to the original domain. It's like inverse. So transform is if we have problem, we transform to another domain, and then we have a solution, and then we transfer back, or inverse transform, to the original way of thinking. So the solution is the original way. Okay, so if from the Laplace transform is we have a problem in time domain, so we use the Laplace transform for transformation, and then the solution we do it the S domain, and then we inverse back, we transform back to the time domain, so the solution in the time domain. So another transform, popular transform in electrical engineering is Fourier transform, and then Z transform, and also wavelets. in our mathematics, we will study about the Fourier and Z transform after the midterm. Okay, so this is the Laplace transform. If we have the linear differential equation in time domain, so the differential equation must be linear. So we can use a Laplace transform. And then this is the in time domain. So we transform it to the S domain or domain S, or the complex frequency domain. So this is the S, but the complex because the S is G omega T. So this is the complex frequency domain. And then we solve the problem in domain S, or in Laplace in complex frequency domain, using the algebra, and then we have a Laplace solution here, and then we inverse back to the time domain solution. So this is the way of thinking about the Laplace transform. Okay, for example, if we have the circuits, the electrical circuit like this one, so we have the input voltage here, and then the current input current here, and then we have capacitor, inductor, and resistor. So we can imagine that we can solve how to find the V-in input V-in or input current by using the ODE. Yeah, we discussed in last week using, because this is we have a two capacitor and inductor, and also the resistor, so it must be using, we can solve it using the second order differential equations. But as you know that a second order differential equation is a little bit, yeah, it's complicated, and yeah, takes a long time to solve it. So we can solve this circuit by using the Laplace. The first one, how to get this one, we can use the first one. We can use the find the input impedance of this circuit. Z-in is V-in per E-in, and then by series and parallel combination rule, we have the Z-in. Z-in is the impedance of this passive component. So the first one, we have a capacitor here, 2 farad here, so we transfer to the impedance. So the impedance of the capacitor is this one, 1 per 2s, and then this is the resistor here, 1 ohm, and also the inductor here, parallel, 4 Henry. So this is the impedance. 1 is for resistor, and 4s is for inductor, so this parallel, and then this one is for the another resistor here, 3 ohm. So we got that this one, Z-in is 1 per 2s plus 4s per 1 plus 4s plus 3. So because of Z-in is V-in per E-in, so we get that V-in in S domain S is this one, Z-in dot multiplied by E-in. So if we have a value of V-in, we can solve this problem. So yeah, it's a little bit, yeah, this is simple. Then we use the second order ODE. Or another case, we can solve this one also. Okay, so this is the basic tool for continuous time Laplace transform. So there are many many requirements if we can use this the Laplace transform. The first one, the first one I said before, that the differential equation must be linear, and then the second is it must be continuous. So the Laplace must be continuous time. So if we if the signal is not continuous, so we use the Fourier transform. So for the Laplace transform, so we transform from domain T, Ft, to the domain S. How to convert from a function in domain T or time domain to the domain S by using this equation. Integral from 0 to unlimited Ft dot E power of minus st dt. So this is the function how to convert from time domain or domain t to domain s. Okay. So yeah, we transfer from domain t to domain s, and then the domain t is the real and domain s is complex. So after that we have to imagine by ourselves this is the complex situation here, complex plane, just like this one. So we have the real axis here and imaginary axis here. So this is just how to solve in the complex plane. This is just a review. Maybe I think you have learned in physics or in maybe in calculus about this one. So here the magnitude of u is x plus gy. Y is this one. This is the y here. This one. So u is here. Okay. And then the phase of u is theta here. Theta is arcus tangen of y per x. And then the magnitude of u is magnitude of r here. And this is this one, the sqrt of x quadrat plus y quadrat. So u is this one, this complex conjugates. U is x minus g y if lies in bottom in minus y axis. This is u in positive y axis, and this is u in negative y axis. Okay, so this is the function I told before. For the Laplace transform, if we transfer from domain t to domain s, so we use this equation, integral from 0 to unlimited ft e power of minus st dt. And then the inverse we will talk it later after we finish the Laplace transform is this one. From the domain s, inverse to domain t is 1 per 2 vg integral for gamma what is it, theta minus j unlimited to theta plus j unlimited fs e power of ts ds. So this is the equation how to inverse from the domain s to domain t. For example, the first one, this is the unit step. Unit step is this one. So if we have the signal start from 0, so this is unit step. I use the difference color here. So this is the unit step. If in x, so this is domain t, domain t here. So t equal if t smaller than 0, so the signal of ut is this one. Ut is 0, and then if t so ut is equal to 0, so this ut equal to 1. Is if t time is similar and larger than 0, so ut is equal to 1. So this is the select this one. So this is the one. So this is the signal, the unit step signal. So how to transform from the domain t domain s? So we use this one. This is the Laplace of ut. So we use this equation. So integral from 0 to theta. This is the ft. And ft is ut. So ut here is 1. Okay. And Laplace transform is from 0 to unlimited. So we start from 0. So here this is 1. And then e power of minus st dt. So this is e minus st dt. So we got that is equal to minus 1 per s e power of minus st from 0 to unlimited. So we can get that Laplace of ut is 1 per s. So this is the Laplace transform of unit step is this one. Okay, so this is the unit impulse. So the unit impulse is like this one. So the unit impulse is just impulse. in t is t0 like this one. So there is a impulse. Suddenly we have the impulse. So we write the impulse like this one, theta t minus t0. So mathematically we can get this one. And then if we make an integral from t0 minus e epsilon to t0 plus epsilon, is theta t minus t0 dt is equal to 1 when the epsilon is larger than 0. So how to transform the units impulse is, okay, we put that ft is equal to theta t, and theta t is impulse. It's just an impulse. So we got that Laplace of the impulse is 0 to unlimited theta t e power of minus st dt. So we got that when t is equal to 0, so e power of minus 0s, so equal to 1. So the Laplace of the impulse is 1. So the Laplace of the impulse t is equal to 1. So yeah, please remember it. And then you have to remember that if we have the specific function in domain t, time domain, and we transfer to the domain s as domain, if we inverse back, we can get the similar results. So it means that the ft and fs are transform pairs. So each ft has the unique fs, and each fs there is a unique ft. Okay, so if you remember, it's like the Laplace transform of unit impulse is equal to 1 per s. So if we inverse, if you have the function 1 per s, so if you inverse transform, so you got that that is a unit step. And another example, if you remember that the Laplace transform of impulse signal is 1. So if you inverse from the function in domain S is 1, so it must be a unit impulse. So it's like this one. So it must be transformed. So another transform pair. So if we have, if you find that this one, the function of e power of minus at ut. So just make integral from 0 to unlimited. E power of minus at, this is the function, dot e power of minus st dt. So we make an integral from 0 to unlimited. This one wrong here. E power of minus s plus a t dt. So the Laplace of this function is minus e power of minus st per s plus a from 0 to unlimited. So we're going to get that this one is 1 per s plus a. So if you have the function in domain, time domain, e power of minus at ut, so the Laplace transform is 1 per s plus a. Okay, and another function is like a tut. So yeah, so if in this case, if you have the problem like this one ut, so you don't need to you can ignore the ut here unit step, because it's just how to express the function in domain, in time domain. So it's like this one. So tut is mean that you you make a Laplace transform of domain of t. The function is t here. This is the ft. So go to the basic equation how to transform is integral from 0 to unlimited ft e power of minus st dt. Okay, so just replace ft using the t here, so we can get this one, t e power of minus st dt. So we use the partial integral here. So integral of 0 to unlimited u dv is uv 0 to unlimited minus integral of 0 to unlimited v du, and then u is t and dv is we make assumption that e minus power of minus st dt. So we can get from this partial integral, we got that Laplace transform of t ut is 1 per s quadrat here. Okay, so this is the Laplace transform of the function ft is equal to t. And then this is for the cos omega t. Okay, for cos omega t, we have to transform, or we have to describe cos omega t in Euler function like this one. See, this is the Euler function of the cos omega t. This is the cos omega t here. So after we transformed from cos omega t to the Euler function, we got that we can replace the cos omega t using these equations. So you can find also for the sin omega t, tan omega t using the Euler function. Euler function, okay. So Euler function from sin omega t. Oops, sorry. Sin omega t. Okay, what is? Okay, you can find by yourself, and then by finishing this integral, we can get that this one is a half of 1 per s minus g omega plus 1 per s plus g omega. So we can get that this one is s per s quadrat plus omega w quadrat or omega quadrat. So we can get that cos omega t transform, and the Laplace transform is s per s quadrat plus omega quadrat. So this is the Laplace transform of cos omega t. Okay. So after this is the basic of the Laplace transform. Then after this we will learn about the how if we use the time shift and also the frequency shift. Okay, I think this is for the introductions. Thank you very much for your attention. Good morning. Assalamualaikum warahmatullahi wabarakatuh.